Okay, then yeah. Welcome everyone to the weekly colloquium of the Instituto de Ciencias Físicas of the UNAM in Cuernavaca in Mexico. Our guest today is Professor Lev Kaplan from Tulane University in the United States. Let me some few words about the vitae of Professor Kaplan. So he did his PhD at Harvard University in the United States, and afterwards he did postdoc as well as at Harvard University and at the University of Washington. And since 2003, he is a professor at Tulane University. And his research interests are in complex quantum systems, I would say, in quantum chaos, quantum information. And Lev, thank you very much for accepting my invitation to join us today via Zoom. And we are looking forward to your talk.
Thank you very much, Thomas. I hope everyone can hear me. Thank you for this nice introduction. It's always nice to be able to visit Cuernavaca, even if, unfortunately, not in person this year. So this is intended to be rather informal talk, so please don't hesitate if you have questions, anything you'd like to discuss, don't hesitate to interrupt, either via chat or just raise your hand or unmute your microphone, whatever you prefer. I'm also happy, of course, to discuss at the end. So the topic for today's talk is transport efficiency in open quantum systems with static and dynamic disorder, and we'll discuss what all of these things mean. So I'll begin with some motivation and overview. Then we'll discuss the basic formalism. And so just in very basic terms, what does it mean to have an open quantum system? How do we treat it mathematically? How we treat disorder, how we treat dephasing, and how we put all of these different things together. Then we want to address specifically opening assisted quantum transport enhancement. And this basically is the question of what are the circumstances in which in an open quantum system, quantum coherent transport is enhanced compared to the transport that you would get incoherently using a classical model. We will apply that to the FMO photosynthetic complex, which is part of our original motivation. And then we will go on to ask a somewhat different but related question, which is when does dephasing aid transport in open systems? Okay, so just to begin with a little bit of motivation, which is not really that important or that necessary for understanding the rest of the talk, but this is just to provide a little bit of context and an example for those for whom this is helpful. So over the past, 15 years or so now, there's been, significant interest in what's known as quantum biology, right? Which is the question of what role quantum mechanics and quantum coherence may or may not play in biological processes, including in particular light harvesting. And it's been observed that both, there are experimental indications and as well as numerical indications that at least in some circumstances, quantum coherence may persist, even in the wet and hot environment that you see in biological systems. Of course, if quantum behavior is present, if coherence is present, that does not necessarily mean that that it's important, in terms of function. That's a separate question, but we're going to talk about all of that. Okay, so kind of the question that one tries to ask in this field is, Again, number one, is quantum mechanics relevant? In what situations is quantum mechanics relevant? And what, if any, is the functional purpose of quantum coherence in natural systems? But for our purposes, we're not so much interested in these specific biological systems. We're interested more in using this as a starting point to ask more general questions about quantum mechanics. So here's a very simple theorist's caricature of the FMO complex, which is found in green sulfur bacteria. So here it's represented as 7 sites. Some models will have 8 sites. As with everything in biology, things are not that precise. But in any case, in this particular picture, so the way you should think about it is light. Each of these sites can carry an excitation, and under normal or natural conditions, the intensity of incoming light is sufficiently weak that you never get more than 1 excitation at a time present in the complex. So physically what happens is you have light hitting the complex, and excitation gets excited, then the excitation can hop from site to site until eventually it reaches a site that's connected to the reaction center. And this is what's called here loss of excitation, but actually the loss should not really be thought of as a loss, because that's what you want to happen. You want the energy to be transferred to the excitation center where the bacteria can use the energy. So, but thinking of this kind of more kind of abstractly as a quantum system, we have kind of a network, right? Which we can think of as a tight binding model, because we have an excitation hopping from site to site. So there are these bonds, there are these hopping amplitudes that can all be different. On each site, you have a different energy. So you have disorder. And also there's dephasing, because you're at finite temperature. And finally, the system is an open system, because there's an opening, at least here, to the reaction center. In reality, there's also fluorescence that happens where you can have decay from any one of these sites. That's not shown in the picture, right? So the important message here is you have a system with disorder, you have dephasing, and you have opening. So you can have all the different complications that you can have in a real-world quantum system. Now, almost a decade ago, when my collaborators, Luca Cilardo, who's in Puebla, studied this particular system, and we're not going to focus on all the details here. So the important thing here is that what's being plotted here is the efficiency on the vertical axis, eta, which is basically the probability of the energy ending up at the reaction center, and as opposed to being lost to fluorescence. And here, this T here is the decay time for coupling to the reaction center. So the shorter the decay time, the stronger the coupling to the reaction center. Okay, and here we have the classical efficiency, and the classical efficiency is the dashed curve. The classical is the red curve, the solid one. The quantum as the dashed, and we're going to the thing to sort of notice is, of course, for weak coupling, for large decay time, there's no difference between quantum and classical. But so this is the regime of where the opening is perturbative, but as the opening becomes stronger, there's a difference. So coherence plays a role, and in particular, at a certain sort of value of the opening, which corresponds to superradiance, and that's when the energy associated with the opening is of the same order as the spectral as the spectral spacings in the closed system, you get this enhancement. So you get this quantum enhancement in the efficiency. Now, if you keep increasing the coupling, the efficiency starts to go back down, and you can think of this as resonance trapping or the quantum Zeno effect, right? Where if you couple too strongly to the outside world, then you never decay, right? And so, of course, this kind of non-monotonic behavior is typical of quantum open systems, and you cannot have this kind of non-monotonic behavior classically. Okay. Now turning to the second slide here, this is just showing that you can do this calculation at different temperatures, and under some circumstances, higher temperature means higher decoherence can actually enhance the transport, and we'll come back to that later in today's talk. So what we want, however, is not specifically just to think about this particular system, but what we like to have is a systematic understanding of quantum transport, where all of the following may simultaneously be important. So you may have disorder, you have an open system, and you have decoherence. Okay, and there are lots and lots of applications, some of which are discussed here. So it's a very big field. We're going to just look at a few select questions. One question we want to understand is, for which values of the opening strength are the coherence effects relevant? Under what generic conditions can quantum coherence enhance transport in open quantum systems? Under what situations can dephasing enhance quantum transport in an open system? And then also, how does the geometric arrangement, such as the dimensionality of the system, whether it's a one-dimensional chain or something more complicated than that, the connectivity, how does that affect the quantum transport? Okay, so there's a lot going on because you can vary the opening, you can vary the disorder, the dephasing, you can vary the geometric arrangement, the connectivity. There's a lot of parameters you can tune, and we're just going to focus on a few specific questions. So to begin with, we start with a closed system, and of course everybody knows for a closed system which is a tight binding model here, we can write down the system Hamiltonian. So this is an Anderson type model, and here we've written down the Hamiltonian for a one-dimensional chain of n sites. Here's the hopping omega, and the little omega j's are the disordered self-energies, on-site energies. Now we want to open up the system, and in general, the way you open up the system is you connect the system to an environment, and then formally, at least, we can construct an effective Hamiltonian where we take the system plus environment, and then we integrate out the environmental degrees of freedom. So this is the so-called effective Hamiltonian, right? It has the original Hamiltonian plus some Hermitian correction plus an anti-Hermitian correction, which can be written down explicitly in terms of the coupling between the system and the various channels in the environment. Now, the thing kind of to note here is that this non-Hermitian Hamiltonian is exact in the sense that 1 over E minus H effective is the exact Green's function for starting and ending in the system, possibly going through the environment. But this non-Hermitian effective Hamiltonian is a funny kind of object because it's an energy-dependent Hamiltonian. So what one typically does is one just first of all often drops this Hermitian piece, and then for the non-Hermitian part, one often just fixes the energy to be, say, in the middle of the band. So this, of course, is an approximation. But now we have a matrix, which is just the original matrix plus an anti-Hermitian correction, which incorporates the coupling to the environment, basically incorporates the decay into the environmental channels, right? And this approximation is basically the same as the Fermi golden rule approximation, but it can be thought of as kind of a generalized version of Fermi golden rule. The opening here may be large or small, so we're not restricted to situations where the opening is a perturbation. So the opening may be large. However, we are restricted if we want to make this approximation to have a continuum that's broad-banded and slowly varying density of states in the continuum. Again, sort of the usual assumptions one makes in the Fermi golden rule. Okay, so again, if you just go back to the simplest example of a linear chain, you may want to couple the last site, the nth site, to the sink. Okay, and that's incorporated here through this rate gamma trap. And in addition, we may turn on some fluorescence, right? So where excitation on any site can decay through recombination. And so that's this term. So this is the effective non-Hermitian Hamiltonian that includes both of these opening effects. All right, so we have at this point disorder and we have opening. The last piece is we need to incorporate dephasing into the model. So of course, that means we have to work with a master equation. We can't work with wave functions anymore. So we have this master equation where we have our closed system, we have the opening, we have fluorescence, and then we add this, and then we need one more term which describes the dephasing. And here, just for pedagogical purposes, we use this very simple Huck-and-Strobel model, which basically says, if you think about the density matrix, that dephasing means all the off-diagonal elements of the density matrix are decaying at a constant rate. Okay, so it means dephasing is happening equally everywhere in the system, right? You can think of this kind of as a very as valid in the very high temperature regime. For finite temperatures, this is actually not true. The rate at which dephasing affects a particular eigenstate will in reality depend on the energy of that eigenstate. So you should have these kind of Boltzmann factors in the model. But the qualitative discussion, as far as the qualitative behavior is concerned, everything that I'm going to say is not really going to be affected by the details of the dephasing model. So we'll just go with this one, which has a single parameter. In this case, the little gamma should be thought of, that's the strength of dephasing, should be thought of as being proportional to the temperature. So then in general, so we have this master equation. So we're supposed to integrate the master equation starting from some initial conditions where, the excitation starts off on some site. But in practice, we're often just interested in the efficiency, which is the probability that you start on a given site and eventually you end up on the reaction center, or you want to know the average time that it takes to reach the reaction center. And these can be computed explicitly by taking just taking the inverse of the super operator here without having to do any numerical integration. So we kind of have these two measures. One is the efficiency, another is the transfer time. However, in many applications, one is interested in situations where the efficiency is high. So the efficiency is close to 1, right? So in those situations, one can sort of treat things perturbatively, and one can show that if the efficiency is going to be close to 1, that means the fluorescence, the spontaneous decay, has to be small, so that most of the time you reach your target, as opposed to the excitation being lost, right? And that certainly seems to be true in these natural systems like FMO, which is why where people are interested in them, because they're pretty efficient. So it turns out that in this kind of perturbative regime, there's actually a nice relationship between the efficiency eta and the average transfer time tau, okay? And maximizing the efficiency eta is equivalent to minimizing the transfer time tau. So without loss of generality, in the following, we will just focus on calculating the transfer time tau. But again, you should think of shorter transfer time as corresponding to larger efficiency. Okay, so what I promised we want to do is to be able to do a comparison where we study the effects of quantum coherence, and that means we want to know what the difference is between the efficiency of the quantum coherent transport versus efficiency of the corresponding classical transport, right? But of course, to do that, we need to define what we mean by incoherent transport, okay? And the way we define it is in terms of this kind of classical master equation that we see at the top of the slide, right? So here, this is a classical equation. The pi is the probability to be on site I, and the t's are the classical hopping probabilities from I to j and j to I. And to construct these objects, we take the dephasing rate to be high, and then we can match what the hopping probabilities are so that they agree with the quantum transport in the regime of fast dephasing rate, right? So in other words, we want to try to do an apples to apples comparison where when we're doing the incoherent transport, the rate is the same. Of course, we're dropping all the, everything relating to the off-diagonal elements of the density matrix, right? All the coherence effects, right? So, so this is sort of our equation. And then, of course, incorporating opening in a classical system is straightforward, right? We just add a term here that goes like the rate proportional to the probability of being on site I, and that's just the rate of decay from site I. Okay. So so this is so this sort of approach is the incoherent approach is often known as as you can see here at the top as the Forster model or Forster equation. Okay, but there's a kind of a better approximation due to Leegwater, and the only difference between the Leegwater approximation and the Forster approximation is that the rates are non-classical. Specifically, for the case where a given site is not coupled to the lead, we just use the same classical hopping, the same classical rate as before. But in the case of where either one of the sites I or j is coupled to the lead, we use this modified rate. So obviously this rate, even though it kind of looks like a classical rate, we're treating it like a classical rate. But of course, it's obviously non-classical, right? In the classical world, if you're trying to hop from I to j, the rate of hopping from I to j should not be affected by the fact that either I or j is coupled to something else, in this case, coupled to a trap, right? So this is a quantum effect, but we can effectively incorporate this quantum effect, if you like. Again, you can think of this as a resonance trapping effect or a quantum Zeno effect that basically says that coupling between sites, between sites I and j is slowed down. The coupling between sites I and j is suppressed if either I or j is coupled to the outside world. Okay, so again, if you find this formula mysterious, one way that you can think about it is you just consider the two-site system and you solve and you solve the quantum mechanics exactly, which you can do because everything is just 2 by 2 matrices in that case. And then you find that this exactly describes the transfer time in the 2 by 2 system. Okay. So this again, it's kind of it's not a classical approximation, but it's a classical-like approximation that incorporates some of the effects of quantum coherence, such as resonance trapping, and in some cases, it may provide a useful approximation for quantum behavior, even when the pure classical model fails. Okay, so here's the two-site kind of toy system that I just mentioned. We have site 1 and site 2. There's some detuning delta between them, right? More generally, we think of this as disorder, but here it's just the detuning. They're just 2 sites in our system. They're coupled by omega. We start on site 1. Site 2 is coupled to a trap. And the question is, again, if you start on site 1, how long does it take to reach the trap? Okay, so in this case, everything can be done analytically because it's just such a simple system. But here, what we do is, again, instead of calculating the efficiency, we calculate the transfer time. Don't worry about the units. The units are kind of arbitrary here, but we calculate the transfer time as a function of the coupling to the trap. Okay, and again, the red dashed line here is the incoherent calculation. It looks almost independent of the coupling. It's actually not quite independent, but on the scale we're looking at it, you can see it's effectively independent of the coupling. Whereas if you look at the quantum behavior, for small coupling, it follows the classical very nicely. That's what it's supposed to do because the rate is adjusted to match for the classical to match the quantum rate. But then as you see, as you open up the system, as you go into the regime of, if you go into the regime of strong coupling to the trap, you see here, you get a big enhancement, right? So the transfer, the quantum transfer, which is computed, using the full coherence of the quantum process, you can see is much faster. In this case, almost an order of magnitude faster compared to the incoherent transport. Okay, and in case you're wondering, what is special about this particular coupling? Well, if you look up here, you can see that this value of the coupling around gamma trap equal 20 in these units corresponds to the superradiance transition. So this is the transition basically where where this gamma, or more precisely gamma over 2, becomes equal to the detuning. And that's the value of the opening at which you have a rearrangement of the resonances. As if you keep increasing, the opening, eventually you have a trapped resonance. So you have a resonance that just lives on site 1 and another resonance that lives on site 2, and they become effectively decoupled, and then transport is suppressed. So here, the transfer time becomes much longer than the classical time. So for very large opening, quantum coherence suppresses transport, but there's this important regime here where quantum coherence actually enhances transport. Okay. So as I said, everything here can be done analytically. In this case, the exact quantum expression for tau for the transfer time can be computed analytically, and the quantum result actually matches exactly the Leegwater approximation. And here you have the classical comparison, so you can see the differences. You have these extra terms here related to the opening, right? And those are the ones that cause enhancement in transport for moderate gamma, and then suppression for very large gamma. again, because everything is nice and analytic, we can read off what is the optimal coupling. We can read off the enhancement factor. And we can also see here, and we'll come back to this point a little bit later, that the dephasing, this little gamma, under certain circumstances can enhance transport. Okay. We can draw a little sort of phase diagram. So if we work in delta, here again is the detuning. So if we fix the detuning, there are two energy parameters that we can vary. One is the dephasing, right? And again, in more general context, this would be the ratio of the dephasing to the disorder, or since dephasing essentially can be thought of as dynamic disorder, this can be thought of as the ratio of the strength of dynamic disorder to the strength of static disorder in the system. And then here on the vertical axis, we have the strength of the opening, again, in units of the detuning, but more generally in units of the disorder strength. Okay, so what we see is when the opening is small, we're basically in the Forster regime where everything is classical. Quantum mechanics really just doesn't matter. You just get classical incoherent behavior. If the opening is very strong, you're in the quantum Zeno or trapped resonance regime where the opening suppresses transport. So here, quantum transport is slower, is less efficient than classical or incoherent transport. But then we have this blue regime, okay, where quantum effects do enhance transport, okay, compared to the incoherent approximation, right? And we can see that this happens when you have this kind of Goldilocks scenario when the opening is not too weak and not too strong, but sort of just right, kind of to match roughly the energy scale of your closed system Hamiltonian. And also we see, the smaller the dephasing. So if you like, the lower the temperature or the larger the disorder, the bigger this region gets, right? So the more disorder you have, the more opportunity there is for quantum mechanics to help transport. Okay. All right, so this was all for a site of, for a chain of two sites, which is kind of trivial, but then we can extend this to a chain of arbitrary length n. Ask the question, how efficient is the transport starting from site 1 and reaching the sink? Okay, so you can sort of write down the answer classically, and you can write down the answer in this Leegwater approximation, which is a pretty good approximation for the full quantum behavior. So actually, in this case, there's no exact closed form answer for the true quantum behavior, but you can look, if you can think about doing an expansion, and you can compare the exact quantum behavior with the Leegwater approximation, and sort of how that behaves, what the next term would be. Okay, but for what I'm going to show in the next few slides, the Leegwater approximation is going to be sufficient for understanding what's going on, right? So we have this result, the transfer time, the incoherent transfer time, and this, which is more or less the quantum transfer time. And we can sort of do the analysis. We can figure out when you have quantum enhancement. You can figure out what the optimal opening is to get the maximum enhancement. And again, you have basically the same kind of diagram. The only difference here being that, it's this detuning delta must be replaced by something proportional to the strength of the disorder in a general n-site system. And basically everything works identically. Okay, and here are some graphs. So some numerical graphs. Now, the solid curve here is classical, is the classical incoherent calculation. The dashed line is the Leegwater calculation, which again is analytic. The symbols are obtained numerically doing the actual, solving the actual quantum problem exactly, by numerically. But you can see that that Leegwater is pretty close. So if you just look, for example, as this, let's say the blue data, it doesn't really matter which one we look at. We see again for weak coupling, this is the decay, this is the transfer time. Again, the solid blue line. This is classical, sort of almost independent of the opening, and then quantum mechanically we see this dip. In this case, only a factor of 2 or so. But you can see this is because it's on a log scale, right? But you can see this enhancements, right? So this is the region where the quantum transport is about a factor of 2 faster than you would expect classically. Okay. And here the horizontal axis is actually scaled, so the opening is expressed in terms of the optimal opening, which can be calculated analytically. And so in this case, we expect the maximum in quantum effect, the quantum enhancement, to be when this is 1, and this indeed is what happens. So we have a pretty good control over everything that's going on. This is again just to show some agreement between analytics and numerics as you make the chain longer. So far we've been talking about the single chain, right? And of course the linear chain is very, very commonly exhaustively studied kind of paradigm system. And again, it has the advantage that you can do a lot of things analytically there, and really, to understand how you tune, how all the different knobs that you can tune affect the answer. But of course, we also want to know, how general is this type of behavior, right? So we try here something completely different. In fact, you can think of this as sort of the opposite of a linear chain. Which is a fully connected system, right? So we have again n sites, but instead of being connected in a line, each site is connected with equal coupling omega to every other site, right? So you can think of this, instead of sort of a one-dimensional structure, you can think of this as a d-dimensional structure in the limit where d goes to infinity. So sort of everything is coupled to everything else. Okay. So as before, we connect site n. Now, of course, here this is symmetric, so it doesn't matter. So we just arbitrarily pick one of the sites. We call it site n, and it will be connected to the opening. And then also we arbitrarily choose some site to be site 1. Where we launch the excitation initially, and then we do the same calculation. Okay, I won't bore you with all the details, except just to say, again, in the simple model, and there are different regimes, but we're interested specifically in the regime where quantum mechanics does help transport. So then we write down what the equations are, specifically in that regime. Okay, so that we can. So this basically means that dephasing, in particular, has to be reasonably strong. Now, dephasing being large compared to the hopping, that's really just a requirement to have a classical limit at all, right? If you don't have any dephasing at all, then you don't really have a classical limit. So then it doesn't really make sense to try to compare quantum and classical transport. So that's kind of your baseline requirement that the temperature, let's say, has to be sufficiently high, and that's always satisfied in these biological systems, for example. But then to have quantum mechanics enhance rather than suppress transport, you also need the disorder and the opening to be sufficiently large. So if those conditions are satisfied, we can write down, again, the Leegwater approximation, which again is a good approximation for the exact quantum transport, and we can write down what the classical transport time is. It's a little bit more complicated than one might have thought in terms of deriving this, but it can be derived. Okay, and then again we can read off when quantum mechanics aids transport, by how much, what is the optimal opening at which quantum mechanics enhances transport, and then sort of you can do these plots. Okay, so again, just to pick one of the curves, again, we're plotting the transfer time versus the opening. Again, for small opening, everything is perturbative. Nothing interesting is happening. When the opening becomes large enough, classical transport doesn't care, but in the quantum transport, again, you have, again, in this case, roughly an order of magnitude faster transport compared to the incoherent calculation. And again, this can be understood in terms of the analytics. Okay, and now I want to come back for just a minute to the FMO complex. So you remember this kind of served as our initial motivation, even though our interests are much more general. But we come back to this. So obviously this is a kind of caricature. So here. This is just a 7x7 Hamiltonian that's obtained, obtained from experimental data. Basically, it's a fit to some data. So you think of these 7 sites, and this is kind of a caricature. Of course, you can see every site in principle is coupled to every other site. But some of the couplings in real life seem to be stronger than others. So like site 1 seems to be strongly coupled to site 2 and not so strongly coupled to any of the others. So that's represented by this blue line here. And so roughly speaking, the connectivity looks something like this. And then experimentalists sort of believe that when the light is captured, it actually is captured by one of these 2 sites, 1 and 6, and site 3 is the one where you go to the reaction center. So this is the system. You start either here or some combination of those, and you do your quantum transport or classical transport, and you exit here. And again, you ask how efficient is that? All right, and so you can do the calculations again without going into into a lot of technical details. We just notice, well, let's focus on room temperature, right, which is sort of closest to where these bacteria actually live. So that's the brown curve. The brown curve again is the transfer time as a function, and this again is a function of the coupling to the reaction center. Okay, so this is the transfer time, and this is the quantum. Okay, and again, the fact that tau is smaller here is telling you that quantum coherence is enhancing transport. Now, the surprising thing, is that this enhancement is still present, even at room temperature. Okay, now, kind of as a test, you might ask, what would happen at really high temperature? And if the temperature is high enough, then you see indeed, that the enhancement disappears, which is kind of what you would expect. If you go to liquid nitrogen temperature, then of course the enhancement is even, the transport enhancement is even bigger. But of course, the bacteria couldn't live at that temperature. So it turns out that kind of, room temperature is sort of just kind of borderline to see, to have a significant effect. Okay. All right, and this is just more things about optimal coupling. How am I doing for time, Thomas? Because I can continue for a little more, or I
You
can
have
really just
about
stop here.
10 minutes if you like.
Okay.
You have about 10
Excellent.
minutes.
Okay, so very good. So this will be enough time to just sort of go through a little bit at least of the addressing this next question, which is when does dephasing aid transport? So again, remember, we're thinking about systems where you have opening, you have disorder, and you have dephasing. And so far, during most of this talk, we've been focusing on varying the opening, varying the coupling to the outside world, and seeing how that can enhance the transport efficiency. So now we're kind of taking a somewhat different perspective on the problem, and we're focusing on sort of tuning the dephasing. Now that's not necessarily something that's very easy to control experimentally, but again, you can think about sort of systems at different temperatures, right? So the question is, so again, it's been known that for a while that under some circumstances, at least, dephasing can aid transport, right? And in some regime, that's very obvious. So for example, if you take a regime of strong disorder, and we live, for example, in a one-dimensional chain, we know that the quantum mechanically we have localization. We have Anderson localization, which means the transport is exponentially suppressed. So clearly in that situation, dephasing or finite temperature is going to be helpful for transport because it destroys the eigenstates and it allows us to sort of overcome the exponential suppression that you would have otherwise. Okay, so that is that's sort of clear and that's well known. And I'll just point out that here in this regime, the opening is not important, right? It's really just overcoming the finite localization length that you have in a disordered quantum system. Okay. But the question we want to ask is what happens if you have weak disorder when the motion actually is ballistic, right? When disorder can be treated, more of a perturbation. Okay, can dephasing still be helpful in that kind of regime? Okay, the answer turns out to be yes. Again, the two-site model is very helpful because we can just sort of read off what's going on analytically, right? So you can see here that if you fix the disorder W and you fix the open gamma trap, then tau is going to be minimized when this quantity over here is equal to square root is equal to W over square root of 6. You can just work it out, simple calculus, right? And so we can sort of read this off. So that means that as long as you have sufficiently large disorder, specifically the disorder is large enough that the opening by itself doesn't give you a large enough width to be able to overcome the disorder, the dephasing is going to be helpful, right? And sort of an intuitive way of thinking about this is you have kind of two kinds of broadening going on here. You have broadening due to the opening, gamma trap, and you have broadening due to dephasing, and somehow you want the combination of these two broadening effects to match the strength of disorder to get optimal transport. Okay. So, this is just to scare everyone a little bit, right? So you can sort of write down some expressions, sort of explicit expressions for the three-site model, and then you still have to, where omega-1, omega-2, and omega-3 are the on-site energies, and then you do the integrals, and then you get some results, okay? And again, I don't want to go into all the technical details, except, well, yeah, to say that yes, one can sort of obtain kind of analytically the behavior for the case of 3 sites. There are several different regimes. The important message, though, is contained in this plot. Okay, so what this plot is telling you, so the curve here is the critical curve W critical, and that means that if W is greater than W critical, in other words, in this blue region, dephasing can enhance transport. So there's an optimal dephasing that exists there. If you're in the pink region, dephasing does not aid transport. So in other words, the optimal dephasing is 0, right? You can't do better than 0 temperature, but here you can do better than 0 temperature. But now again, we see this sort of connection, right? So the critical disorder that determines whether or not dephasing aids transport depends in this very simple way on the strength of the opening. So knowing the strength of the opening tells you whether, you know, how strong the disorder needs to be in order for dephasing to be able to aid transport or not aid transport. And then you can figure out what the optimal dephasing is. So again, you have these 3 things happening: the opening, the disorder, and the dephasing. But again, the key point, without sort of worrying about all the math, is that one can sort of understand what is the regime where dephasing can be helpful for transport. And then one can generalize this for arbitrary. Once we understand what happens for n equal 2 and 3, one can generalize. One gets kind of a scaling for large n, and there are these different kinds of regimes which one can work out. And I want to go to the summary. I think I'm right on about on time here. So I think what I tried to communicate today, first of all, for those who may not be too familiar with it, we have this non-Hermitian Hamiltonian formalism, which is, you know, very powerful general framework which you can study quantum systems that have opening and disorder and dephasing. And then we can look at how these different things, what the interplay is between all these different effects. We can see that quantum systems can display very non-trivial behavior as the opening sizes varied. And in particular, you can obtain very strongly enhanced coherent transport near the superradiance transition. The effect survives at finite temperature. The temperature is not too high compared to the energy scales in the Hamiltonian. In sort of simple models, one can obtain analytic results. And in fact, one can obtain linear analytic results in sort of these 2 opposite regimes, the linear chain and the fully connected network. And then the fact that sort of the physics is kind of similar in these 2 opposite regimes suggests that that this kind of behavior is actually much more general. And in fact, taking this kind of realistic example that exists in nature of FMO, we can see how opening assistant quantum transport can work in practice. And then we also have studied the regime of noise-assisted transport, and we found that whether noise assists or suppresses transport also depends very strongly of the degree of opening. So again, if there's kind of a one-line conclusion, one-line message that I want to communicate, is that, you know, treating the opening properly is important, and you know, one can't always sort of just rely on one's intuition obtained from, you know, treating the opening perturbatively, which is kind of the classical way to think about these kinds of systems. So I'll stop here. Thank you very much.
Okay, yeah, thank you very much, Lev, for this very, very nice, very interesting talk. Are there questions, comments from the audience?
I have a question.
Yes, Thomas, go ahead.
Well, first of all, hi Lev, happy to see you
Hi,
here.
Thomas, good to see you.
Look, I'm not worried about the substantial content of what you say, but just about the question whether it is quantum or not. Super radiance, I guess Weaver has shown that at least he can have mazing with a completely classical electronic system. So, and I believe the same holds for super radiance.
Right.
Then there are all these experiments on localization, Anderson localization, including with microwaves. And I mean, again, it somehow seems that these are wave effects rather than quantum effects.
Yes.
Now, what one strictly wants to call a wave effect is always a question. I just remember that the first marvel I was taught was tunneling, and at some point it was quite obvious that elastic waves do it all the time.
Yes. Very good questions. Thank you, Thomas. So yes, so as I said at the very beginning, everything that I was discussing here is in the single excitation regime, right? So we're never thinking about particle-particle interaction. So all the quantum mechanics is single particle quantum mechanics, which of course is just wave mechanics, right? So as you say, that's kind of a philosophical point, right? But you could certainly say that single particle quantum mechanics is classical. Maybe you wouldn't want to quite put it that way, but you would certainly say that single particle quantum mechanics is just wave mechanics, right? So the distinction is between wave mechanics versus particle mechanics or ray mechanics, right? So the comparison is between coherent and incoherent, and indeed, if you think about classical waves, you can you can formulate that in the language of classical waves as well. So there's nothing uniquely quantum about that. It's really just about coherence. Now there certainly is a lot of interest in extending these ideas to to sort of multi-particle systems, right? And as I said, for one reason for focusing on single particle is it seems in systems like FMO, you really are operating in the single particle regime, but obviously in other systems of interest, interactions are important. And that's certainly, I didn't have time to talk about that today, but that's definitely very interested. As far as super radiance, there's sort of also funny terminology there. There's sort of two types of super radiance. There's sort of multi-particle super radiance, and there's single particle super radiance, which again can be thought of as classical wave super radiance, right? So the super radiance I'm referring to here is the single particle or classical wave super radiance, right? But again, yeah, there's definite, so for super radiance, all of that is sort of well understood that there's single particle and then there's multi-particle. As far as these kinds of transport questions, I think there are a lot of open questions as far as how all of this gets modified when you do include interactions. So some kind of a lengthy answer, but I hope I, clarified some things that may have been confusing.
Okay, are there further questions, comments from the audience? I have a question, Lev. So at the end of your talk, you showed these results for one-dimensional chains, which are disordered, and yeah, you're now showing exactly this this figure You mentioned that at some points dephasing is aiding transport, and at some points dephasing is slowing down transport. Yeah, can I understand that the result which you're showing here does not change with the size of the system? So my confusion is that if I understand correctly, in one dimension, all one-dimensional chains are in the limit n to infinity. They are in the regime of Anderson localization.
Yes. Well, that's so the n does appear here, right? So you can see,
Okay.
so you can see here, right? So
Okay,
all
there.
of these plots, yeah. So there's sort of a trick here. There's
Okay.
a rescaling. There is a factor of n.
So this I did not get. Okay.
So the n is kind of small here, right? But these curves look like they're on top of each other because they've been rescaled.
Okay.
The localization, the localization criterion, of course, in one dimension looks like W bigger than I guess omega over square root of n, right? So so one has to be sort of careful about that. So in other words, one can have for any given n, one can choose disorder that's strong enough for, so that disorder and dephasing are playing an important role, but not so strong that you sort of become localized, okay? That's kind of a little bit, more explicit in, I guess over here. So again, I didn't talk about the different regimes because it's just sort of too messy. But the point here is that what I'm calling the strong disorder regime is the localized regime.
Okay, I see.
But the point here is that even in what we're calling the moderate disorder and the weak disorder regime, where you don't have localization, dephasing can still aid transport. Okay, the optimal dephasing, of course, is going to be different in these regimes. So roughly speaking, the stronger the disorder, the stronger the optimal dephasing is going to be to overcome that disorder. But the basic message here is that, dephasing does aid transport even in, when disorder is weak.
Okay, I see. Thank you very much, Lev.
Sure.
Are there further questions?
I would have another one if nobody else has one.
Yes, Thomas, go ahead.
This is a little more constructive. All this work, I'm sure, of our common friend Thomas Brosen, where he first shows many body localization in one dimension, and then he shows that it's pretty unlikely actually to exist in the infinite limit. But I don't even know, but I would expect the dephasing would have a strong effect on this, let's say, finite size localization situations. Do you think that these things, at least in one dimension, would easily apply to the one-dimensional many-body problem, which definitely isn't one-dimensional in that sense?
Right. So, so applied in what sense? Yes, I think it's certainly interesting. I don't have an answer in the sense that, I don't know what.
But I guess maybe
happened, right? I'll just say I think it's something very interesting to explore.
So maybe we should try to have a discussion with Thomas about this matter.
That would be great. That would be great. And I see in the chat.
Yes, there is a question from Ricardo and Cheita. Does entanglement between sides play a role in this formalism?
So I guess the short answer is yes, right? So in when we're doing when we're doing the quantum calculation or the coherent calculation, right? Everything, all the sort of the correlations are in there in the sense of the off-diagonal elements of the density matrix. They're all in there. Yeah. So a way to think about it is that what's different between the coherent calculation and the incoherent classical hopping is the entanglement or correlation between the sites. That's right.
Okay. Carlos Gonzalez is asking a question. What about systems with long-range interactions in 1D? Do they show enhanced transport with dephasing?
Yes. So that's that's a good question. We're actually sort of studying now, something in something in that direction. In particular, if you think of coupling through an electromagnetic field, if in the simplest case, you can just think about dipole-dipole coupling. You have an interaction that falls off as 1 over distance cubed, which is a kind of long-range coupling. So I think so the answer is yes. However, there are other things also also to be taken into account. But I think those are very interesting. That's kind of another knob, right? So that one can, right? So we've talked about opening disorder, dephasing. Of course, one can talk about many body interactions, right? And here one can sort of think about the range of the interaction. One has to be careful again because it's kind of a big dimensional space of problem. So kind of what you're keeping fixed and so on. Again, there are different regimes, but certainly there are regimes where this can be will be relevant. One thing about this sort of dipole-dipole coupling that's makes it a little bit maybe non-generic, or maybe it is generic, I don't know, is that in addition to the real coupling, which goes as 1 over distance cubed, you also have a non-Hermitian interaction induced by the coupling to the electromagnetic field, and that looks like the kind of the all-to-all coupling, where each site is coupled to every other site because the coupling is coherent. So one has to be careful about kind of separating those effects, or at least in a computer. One can kind of look separately at the contribution of the Hermitian and the non-Hermitian terms, which one can't really do, in the experiment in nature.
Okay. Are there further questions, comments? I have another question which goes in the same directions as the question by Thomas and Carlos. When we think in this application of this FMO complex, if I understood correctly, you consider an excitation with a fixed energy, and the energy of the excitation is not changing at all in the complex. Do dissipation processes play a role in these systems? Sorry,
can you just repeat that last thing you said?
Does energy dissipation play a role in the system? So if I understand correctly, you consider everything at a fixed energy. And yes. So my question is, how will the things in general change when you take into account energy relaxation, energy dissipation?
Yeah, that's a good question. So I was saying kind of what we're thinking of, what we've been sort of showing here is sort of just pure dephasing, right? In this kind of Haken-Strobel model, which doesn't take into account, yeah, exactly. Energy relaxation. From what I have seen, for sort of, again, it's hard to generalize because there's so many different parameter regimes, etc. Right? But but at least in the cases that I have sort of looked at, there, the qualitative behavior is still similar. But that does not mean at all that there isn't a regime where the relaxation processes are very fast and compared to, again, the transport time, and where that becomes kind of the dominant effect that one needs to consider. Yeah, so that would actually, would definitely be, interesting question to ask, kind of to explore, at least getting a rough idea again of, what is the parameter regime where that kind of effect, either matters or doesn't matter, right?
I agree. Okay.
Certainly at sufficiently low temperatures, it's clear that it will make, will make a big difference.
Yes. Well, I think also when you start on thinking on these relaxation processes, I think you can also, other questions become interesting. Let's say if you can define in a chain something like a local temperature, because then you have something like real non-equilibrium in the system when you think on energy dissipation, relaxation. And can you define a local temperature? How does the behavior compare, let's say, to classical Boltzmann transport theory? These are, I think, related or new questions which arise when you think on these kind of things.
Yeah, definitely.
Okay. Yeah, if there are no further questions, comments, counter proposals, then we, thank you again, Lev, for this very, very nice, very interesting talk. Thank you very much for joining us via Zoom.
Sure.
Yeah, I think we all would have enjoyed that we were in person at the institute in Cuernavaca.
Sure. So I appreciate the invitation. Yeah, it's a bit unfortunate that that's how things are these days. Hopefully next year maybe things will be better. I guess the advantage of an in-person visit is we would have the opportunity, obviously, for further discussion along all these nice direction that that you and Thomas and others have suggested. I'd certainly be happy to continue, discussion with anyone, offline about, these different possible directions.
Okay. Thank you very much, Lev. And
thanks again.
And see you next week.
All of you. Bye.
Bye.
Hope to see you here soon.
Yeah.